I'd like to start by acknowledging my co-authors, which are Alice, Émilie, Michel, and Stéphane. And I guess what I will be talking about is a segmentation problem that we get in bioinformatics, and that involves count data. And I think the problem we are dealing with is fairly simple. Basically, we have a tremendous amount of data, and n in our case might be, in the smallest case, 10 to the power 5, and in the worst case, 10 to the power 8. And so in those cases, essentially, if you want to do maximum likelihood or anything like that, even the algorithm described before are usually a bit too slow for any practical application. And what I will be talking about today is how you can speed up this a bit and essentially get to a problem which is an order of magnitude smaller. So let's say that if you start with a problem of n equal 10 to the power 8, you will go to a problem of 10 million and not 100 million. Okay, so the data we are looking at are next generation sequencing data, and here is a small example of that. So here we are looking at the genome of the yeast. So what I represented on the x-axis is the position on this genome. So it's a rather short genome where you only have 200,000 position. And here I represented the measurement that we get, which are count value, and here I just square rooted so that we can see something. And I mean here, even if you're not familiar with this data, I think it's quite clear that trying to detect some change point is a rather natural thing to do. And typically here we have region where the intensity is pretty high and others where it's pretty low. And these peaks typically correspond to gene, and you want to detect where they are and where the boundaries are depending on the condition you're looking at. And I think the key features that I want you to see on this particular profile, which is very striking in this example, is this. So here, if you look from this point to this point, essentially the signal is flat, meaning that you get a row or a stretch of value where you get exactly the same measurement. And I think so what I will be talking about is the rather intuitive idea that if you're looking for the optimal change point in terms of, let's say, maximum likelihood, it does not make sense to have any change point in that region. And that essentially you could probably simplify the problem by just saying here, well, it's not meaningful to look for any change point here, so we can maybe compress the data and still be able to recover the maximum likelihood estimate segmentation. And so I guess this intuition is rather clear, and I think the reason we think that is essentially if I consider some data like this, and then I have a plateau like this. Yeah, we basically, at least it's very clear, if you put a change point here and a change point here, if indeed the signal is flat here, it really doesn't make sense to cut again this region in two. So this is fairly obvious for most models, but this result is clearly not sufficient for any practical algorithmic application. What we need is something different. So I will take the same data, and what I need to have is something of this sort. Assume I have a segmentation in two with a change point here, and the question is, whatever the data might be before, whatever the data might be afterwards, can I guarantee that this particular segmentation will never be optimal? And if we can show that, essentially, we will be able to discard all of these regions a priori, so prior to using any dynamic programming algorithms such as PELT or the prune DPA. Okay? So that's the main idea, I guess, of the talk. So here is just a slide to say that the reason we're looking at this data is because we are looking for some interesting biology. So typically, if you're looking at DNA-seq, you would like to find amplification of the genome or deletion, which correspond to possibly genes involved in cancer. And if you're looking at RNA-seq, then you are interested in finding genes and trying to find whether the boundaries of those genes might slightly change from one condition to another. Okay, so here is just the problem we have. So it's, as I said, quite simple. If we just take the raw data, give it to any exact algorithm that we might like, and segment it. If we have 10 to the power 8 data points, then it will take forever. And so our idea, I think, is pretty simple. That, as I said, you can essentially show that you don't need to consider change point in these plateaus. So you can first compress the data, and this is an extremely fast process because you just need to count how many times you observed a particular value in a row. And if you do that, so if I call large n the size of my profile at the beginning and small n the one afterwards, what I hope to get is that if I'm able to reduce the size of the profile by a factor c, I hope to be at least c times faster at the end. And that is because essentially compression is linear, and in fact it is so simple that it's almost a free thing to do. And the only thing you need afterwards is basically a weighted segmentation algorithm to take into account that certain data points have a larger weight because you've observed them several times. Okay, so now I will quickly talk about the statistical model that we've been using for this data, which is a negative binomial model. So it's a fairly simple model, I must say. So what we consider is that we have some data, and we want to segment this data, and we have change points, which I will call tau j and tau j plus 1. And these change points delimit segments from here to here, for example, and these segments are called j. So our data points are simply y1 to yn. And what we're looking for is for S segmentation, let's say in k segments. And in each segment, the model is really simple. So we say that we observe IID observation following a negative binomial model with a parameter pj, which essentially corresponds to the intensity of the signal in that region, and a parameter phi, which is basically the overdispersion and which is global to the whole genome. So even with such a simple model, you already have some problems. So the first, which I will not be talking about today, is how do you get phi? And, well, you can come up with various ways to do it, but essentially here I will assume that we know phi, or that we have a good way to estimate it. The second question, which I will be talking about a lot more today, is how do we recover the segmentation which is optimal with respect to maximum likelihood? And the last problem I will quickly talk about is how can we actually select the number of segments that we want. Okay, so now I will talk about this. So what I will be talking about is actually valid for quite a lot more model than just this one. So I will go to a much more computationally driven slide. So the assumption that we need to show that essentially when you have a plateau, you don't need to add any change point in that region is this framework. So we still consider that we have some data, whatever they might be, integers or whatever. We're still looking for segmentation going from 1 to n, and we want to find some change point, tau j and tau j plus 1, and we're looking at some segmentation in k segments. And what is really important here is the shape of the function that you want to minimize. So essentially, the way you measure the adequation of your segmentation to the data is a sum over all segments of this segmentation, and the cost of each segment is a minimum over certain parameter theta j of a sum from tau j to tau j plus 1 of a function gamma, which has two parameters, yi and theta j. So I will make a few notes about this. So essentially, we have no constraint on what the function gamma might be, and also no constraint on what the parameter theta j might be, so it might be multidimensional. I think the really key thing is that here we have a sum, and then the number of parameters per segment and the actual shape of the function we try to minimize is not that important to show that indeed you will not have change point in those regions. Okay, and in fact there are quite a few models that would fall on this, would guarantee these assumptions. So another way to see the problem is, rather than trying to find change in the intensity of the signal, would be to consider this as a density estimation problem, and we could do that with irregular histograms as proposed by Rosenholk in 2009, We could also consider that we have a Poisson model, like each segment has one parameter, which is the intensity of this Poisson distribution. We could have a negative binomial model where we make where both p and phi change with each segment, and many others. And I think really our goal here is really to optimize this criteria. So, which is typically minus the log likelihood, so we want to recover minus the log. The best segmentation with respect to maximum likelihood. So, if you want to actually prove that you don't need to put any change point in a plateau, so it's a rather, the proof is not so long, but it's a bit tedious because essentially you need to consider different scenarios of what could happen in the data. So I will just quickly describe one example, which I think give a pretty good idea of what is happening. Okay, so let's assume that we have some data. So here I make no assumption on what the data might be. The only thing I know about the data is that between two positions, T1 and T2, essentially the signal is constant. And now I will only consider segmentation in two segments. And so I can consider a partition of the data going from 1 to tau and from tau to n. And I mean, then you can obviously compute the cost of any of these segmentation, and it's simply the sum of the cost of the first segment, which is this, and the sum of the cost plus the cost of the second segment, which is that. And I think the key thing to see here is that when you move tau, there are too many things which are moving at the same time, essentially because you are minimizing here. So meaning that if I slightly move tau to the left, I will have to change the value of theta 1 and the value of theta 2. And so this is somewhat the problem that we have, but essentially we can postpone this minimization and see what is happening. So I will quickly do it here. So if now I consider that the value of the first segment is theta 1 and is fixed, and the value of the second segment is theta 2 and is fixed, you have three terms in your cost. So you have a first part which corresponds to the cost of your data point before T1, which is here. And so this part, if theta 1 is fixed, is constant. You have the equivalent of this, which is here, which is the sum of the cost of the loss function afterwards, which is also, so this is for I superior to T2. This is also a constant if theta 1 and theta 2 are fixed. And the last two terms which are of interest here is that here, as the data point are all the same, here we get exactly tau minus T1 gamma of y T1 theta 1. So here we are essentially saying that in this part of the signal up to tau, which is here, we just sum tau minus T1, the exact same term, which is gamma of y T1 theta 1. And in the other part, we have exactly T2 minus tau term, which are exactly the same. So essentially this. We have T2 minus tau of gamma y T1 gamma 2. Okay. And so once we've done that, the key thing to see is if you think of this, so we sum this term, this term, this term, and this term, and we get the cost for fixed value of theta 1 and theta 2. But essentially, this is a linear function of tau. So it means that if you consider the cost as a function of tau here, when you move it from T1 to T2, it's linear. So it means that the minimum of this function is at one end or the other. And meaning that it's always, what we can guarantee is that a priori, we don't know whether the best segmentation will have a change here or here, but it's most probably not in the middle. And so essentially using that, we can show, and doing some more examples, you can show that the cost of this segmentation is always worse than one of these two, meaning having a change point at T1 or T2. And so another important thing to see, which we'll explain something later, is that we only have a min. So intuitively, what we could have hoped that in fact, putting a change point in the middle is worse than both. But essentially, this is not true. It's worse than one of the two. OK, so once we have this result, so here is a schematic representation of that. So essentially, what I'm saying is that if I have a change point here, and in between this cross and this cross, the signal is flat, it's always better to either put the change point at this end or at this end. And in other words, what we can do now is that if we consider a very simple example like this one, where we have plateaus, essentially mean that this particular change point we don't need to consider, this one also, this one also, this one also, and so on. And so rather than to consider this profile, we'll consider the compressed version of this profile, which is simply saying that we observe 1, 1, 1 time, 2, 0, 2, 2, 4, 0, and 2, 1. And so the compression, so going from this to this, is obviously very simple and extremely fast. And what we expect to gain from that is that, well, if you're using a quadratic algorithm, if you get a reduction of C, so if small n over n is C, you expect a runtime ratio of C squared, so quite a large one. And then I think the key question is, what do you expect to gain when you're using a linear type algorithm? So typically like Pelt or the Kroon DP. Essentially because these two algorithms, in the course of the algorithm, they are pruning the set of solution. So let's say if they were really smart, they should be able to catch that you get those plateaus and that it does not make sense to have breakpoint in those plateaus. And as much as I like those algorithms, I'm afraid to say that they essentially don't see it. And I think the reason is coming from the proof, which is here we only have a minimum, meaning that we only know that this one is better than this one, or this one is worse than this one or this one, but not both. Okay? So how much time do I have left? Okay. So here a very quick side to say that Alice and Emilie have been working on how to select the number of segments, and basically their work is inspired by the work of Birger and Massard. And at the end, what they get is a penalty such as this one, which essentially penalizes the number of segments as the number of change points increase. And our goal is then to recover the maximum of this, which is basically we want to recover the best segmentation with respect to this penalized log likelihood criteria. And the only thing which is a bit tricky here is that we only know the shape of the penalty up to a factor, and you need to calibrate this beta using the slope heuristic, which is presented in this paper. And in practice, at least for negative binomial model, we have good performance for that, but I will not talk too much about this. Okay, so now I will go through some examples to show that it's doing something meaningful. So here, I'm going back to the data I was looking at the beginning. So here we basically implemented this compression scheme and then a version of the Kroon DPA, a generic version of the Kroon DPA. And so here we have a bit more than 10 to the power 5 data points, and with this generic implementation, we get a 4-minute runtime to process this data with k max equal 500. And we recover a segmentation in 100 change points using the penalized criteria that I just described. And the good thing here is that essentially all those breaks more or less correspond to known genes. So they are somewhat validated by our biologist colleagues. And I guess here is just to show that you need to carefully choose your model when you're analyzing some data. So here, if you take a Poisson model, for which you can also do the compression and then selection of the number of breakpoints, you essentially see something like this. And you don't need to be a biologist to see that it clearly does not do what you want him to do. And so that's why we've ended up choosing a negative binomial model for now, rather than a Poisson model. So here it's just a slide to convince you that indeed, if we compress the data, we get a speed up in terms of runtime. So what I plot here for different signal using the exact same package, so the generic version of the PDPA and negative binomial model. Here I plot the compression ratio, here's the runtime ratio, and what you can see that they more or less fall on the x equal y line, meaning that if you compress the data, you indeed get a speed up. And now the last question that I want to answer is to empirically show that essentially pruned algorithms do not catch, that you should not put breakpoints in those regions. And for this, I did a simple experiment with a pruned DP, but it's essentially the same story with spelt. But in that case, we are looking at data where the number of change points is very small, so pelt is not the ideal algorithm in that case. But essentially, I'm using this time the CGH-seg package, so using the L2 loss, and I'm using an irregular histogram model. So the first thing I did is I simulated some Gaussian data, so Gaussian noise. So typically in this data, you have no plateaus. Each value is different from the previous one. And here just represents the runtime as a function of the length. So we can go, let's say, up to 1 million data points with a Kmax of 500. And we would be able to do that in 100 seconds. And so now the next thing I will be doing is to do the same thing with real DNA-sec data where you have plateaus. And so in that case, typically, if indeed you don't need to put any change point in these plateaus, then you would expect the pruning to happen much faster and to be faster than this curve. But in fact, it happened that you have the exact same speed. And in other words, when you're looking at data with plateau, the pruning does not happen faster, meaning that essentially we completely go over this region without doing any pruning. And this is what you get if you do the compression. And essentially, if you do that, you can see that you can go, so here is 8 million data points, and you can do 8 million data points with Kmax equal, let's say, 500 in a bit less than 50 seconds. And so if you continue with this line, you see that you can essentially analyze in a reasonable amount of time 10 to the power 8 data point. Okay, so these are other examples. So this was just one DNA-sec sample, so here are others. And you can see, so the green line is always much lower than the one without the compression. This is an example where I go up to, so it's DNA-sec data. We expect very few change points in that case, but we have roughly 80 million data points. And if we take a Kmax of 100, we can do that in a matter of minutes on a laptop. Okay, and so to conclude, so I think here is a sketch to describe what we've been doing. So essentially what I was saying is that if you have plateau in the signal, it's probably worthwhile compressing this data. And if you do that and then apply your favorite exact algorithm, so it can be PELT, it can be pruned DPA, it can be standard dynamic programming. By doing this, you will still guarantee that at the end of the day, you will get the maximum likelihood estimate and in a much faster amount of time. And here are some conclusions. So this is just what I said. So the compression scheme is valid for basically many models and also many algorithms. If you first do the compression and then use an exact algorithm, you will get the maximum likelihood estimate. So as I said, it's valid for a reasonably large class of loss function. It leads to a speed up of the total runtime, even with prune algorithm, essentially because they do not capture the fact that you should not consider plateaus for change points. And you can, as I showed in the last example, run this on more than 10 million data points and still get some result in a matter of minutes. Okay, so here I would like to acknowledge all the people I've been working on this. So here are my co-authors, and here are different people I've been talking to about this. And I would also like to thank you all for your attention.
I fully understand your paradigm, and I guess it's great that you came up with a one-shot algorithm that combines both goals: get rid of the plateau constraint and be quick and as exact as possible. I understand vaguely why other exact algorithms wouldn't be able to inherently do the job. What I did not understand, but maybe it's a completely naive question, is something like a two-step approach. Could you try to get rid of the plateaus by something which is not exact, but good enough to capture these obvious breakpoints into and off the plateau, like a simple, I mean, maybe a refined binary segmentation method. And then, after having gotten rid of these plateaus, use an exact algorithm like yours?
Yeah, so essentially, I mean, even if you're doing binary segmentation, and assuming that with binary segmentation you're looking for an approximation to maximum likelihood, then essentially you can also discard the plateau.
Right.
So you can essentially you could compress the data and then run binary segmentation.
No, then run yours.
What?
Compress it by binary segmentation and then run the exact fast version.
Okay. No, what I would do is more compress the data and then run binary segmentation. And this way, because basically what I'm saying is that by compressing, you're guaranteed that you will not remove any interesting change point.
Okay, so it's the other way around. The challenge is in order to have a method that is also...
Yeah, so you compress and then you use what, I mean, depends, but if you like binary segmentation, or if your data is good, then I would first compress the data and then run binary segmentation. Possibly in that case, the gain in speed would not be that great because, I mean, a good implementation of binary segmentation runs in a matter of seconds, even for 10 to the power 7.
Right.
But still, you could do it, and you would just win the space in memory, basically.
There are more questions. The plateau that you observe in the data, are they, so it can be just that actually there is a constant behavior there, or that there is missing data, because a lot of time in sequencing, because near centromeres, because things were not sequenced properly, you don't get...
Okay.
So my question is, in these kind of cases where you have plateau that are, you see that the data is much lower, the counts are much lower just because it's missing. From your experience, would it be better just to say, okay, because you can know where these missing plateaus will be, just to say, okay, these two, like the range of these missing places are what I call change points that come from problems in the data, and then just remove it and
in fact, this is what I've done here. So typically, we don't expect to get many reads in the centromeres. So typically here, what I'm looking is only one part of the chromosome. So I'm looking at the data from one end of the centromere, removing this problematic region, and then considering the whole profile after the centromere.
So the plateaus that come from missing data, you remove completely, and then you do the change point, or?
Yeah, you first compress. So essentially, you remove the plateau, or you don't remove them, but you compress them to one data point, saying that you've seen so many zeros or so many 1 in one shot, and then you run the segmentation. And then I agree that in data like this, typically in the centromere, because of many difficulties, you don't get so many reads, but usually you just exclude this region, meaning that here so here it starts at something like 25 millions, and so basically I've excluded this part. I only consider the signal from this position to the end, because I know that in the centromere we get a stretch where basically all the signal that we get is crap.
Just a question for at the end, I think you used the negative binomial model for
Yep.
Did you include an overdispersion term, or didn't you do it?
Yeah, we have an overdispersion, and actually I think it's...
But this is local, right? The overdispersion term is local?
No, in our case,
it was a global term? Because
but we can make it local.
Okay.
And and typically taking into account the overdispersion is the reason why when you go to the Poisson, you get something which is really weird, because the data is, I mean, you have some clear overdispersion in the data.
Yeah, this is not a very well formulated question, but the underlying process in these problems is often very non-homogeneous. That is, if you have an idea of a baseline process without the whatever signal you're trying to detect on it, one could imagine, I don't know if it actually occurs, that the baseline rate dips at a place where it looks as if you've got a plateau, but in fact, relative to what you're expected, there's an increase in the relative rate relative to the baseline. Do you have that problem, or do you just...
Well, in some cases we see this problem, and I guess So typically the good setup for this would be to have some reference. So typically in the case of DNA-seq, we also have normal samples. And with these normal samples, we can somewhat evaluate how many data we expect at each point. And a simple way to take this into account in our model is, where was that? Yeah, I can't find it. Yeah, it's here. Yeah, so to take this into account, a good way or a simple way would essentially be to add here a weight for each data point, saying that, well, at this particular position, given all the normal that I've seen, I expect to see if everything is normal 2 and not 3. And if you do that, essentially, you could still be able to compress the data. But the problem is essentially that you need sufficient amount of normal to calibrate those weights. Yeah. But you could do that. And I agree, it's clearly a problem.
Okay, but brief last question. Just a good comment. There's a Tom Hardcastle in Cambridge Process Department. So we develop a basic, which in there we got segmentation. So it you consider your prior information rather than weighting. But the speed may not faster like yours. I think it's better than the weighting. So you give your Bayesian prior information for the clarity.
Okay, yeah. Okay, yeah.
Useful.
Yeah, well, here I really did not discuss the model that we're using, clearly. I'm just saying that, yeah, from a purely computational point of view, if you think that this model is correct, then you can speed up things. But yeah, the question of which model is the best one, I think is a totally different question. But yeah. And typically if you have a Bayesian prior on, so typically if the likelihood include a prior, I think the compression scheme essentially does not work because the prior would include some terms involving the length of the segment. And then you will disrupt the linearity here, so you will no longer have a sum of something, and so everything will fall down. So you can no longer guarantee that you have to remove those plateaus in the first place. So, okay.